Good afternoon, everyone. Myself Nilmoni, a research scholar at IIT Kharagpur. I am a PMRF NPTEL TA for the course Fourier Analysis and its applications, and which is taught by G.K. Srinivasan sir. And yeah, this is an extra class for this entire course, and this is the last class. And today we will see what is remaining part for this course. So mostly we will see the convergence of convergence of distributions. Uh, Sequentially continuity of differentiation and continuity of Fourier transform, and then Fourier Poisson summation formula. Okay, so let us start, and finally we will solve some problems related to your Poisson summation formula, and in between we will solve some problem uh, for continuity of Fourier transform, continuity of differentiation, and okay, let's see. So convergence of distribution, right? Okay, so this is an extra season. Okay, so first convergence of distribution. Okay, distribution. So before that we have learned convergence, weak convergence in Hilbert space, right? And this convergence is more than weak, more than weak. Okay, so in sense of convergence, this is more than weak than so your convergence in weak convergence in Hilbert space. Okay, so one thing you can notice, the space of distribution, or uh, in tempered distribution, this space is basically dual space, right? Dual space to the locally convex topological vector space, uh, Schwarz space SR, and so then it contains the weak star topology. And let us define this notion of weak star sequential convergence. Okay, so definition, like you know, similar type definition we have defined earlier. Uh, a sequence u nu, so nu you can just infinity of a tempered distribution said to be said to converge to some limit u quickly if for each g belongs to SR, and we have this. So for tempered distribution, we know what is the meaning of this. Uh, okay. So now, yes. So question one. So that sin nu x is tempered distribution. And sin nu x converges to just weakly 0 as nu tending to infinity. Okay, so let us solve this. Now this is simple, right? Your sin nu x is basically bounded, and therefore this is in L infinity R. So this is a tempered distribution. Okay. And now what about second part? So to show sin nu x, this goes to 0 weakly as nu tending to infinity. Okay, let us see. So consider, so let G belongs to SR, G belongs to SR arbitrarily, then consider sin nu x comma g. This is what? This is basically this is integral gx sin nu x dx, and then what you will do, so 1 by 2i gx e to the power I nu x dx plus 1 by 2i gx e to the power minus I nu x dx. This is minus nu g hat, the Fourier transform, right? Both Fourier transform g hat nu. And one thing, see, since g is in SR, so g hat also will be SR, right? So limit this goes to 0, so goes to 0 as nu tending to infinity. More generally mod nu tending to infinity. Okay. And this is basically equals to 0 comma g for all G belongs to SR, and hence zero weakly as to infinity. Okay. And one thing, okay, so question 2, so that converges weakly to the constant 1 to infinity. Okay. So again, this exp minus x square by n, this is 1, and therefore exp x square by n, this is in L infinity R, and so exp minus x square by n, this is a tempered distribution. And now let G belongs to SR. So we want to show this converges to 1 weakly as n tending to infinity. Be arbitrarily okay, this is okay. Now how to deal this? Okay, so now see, this goes to 1 pointwise for all x. Now this gx is equals to mod gx, and g belongs to your SR, and this is in L infinity, so this is integrable, right? So sorry, not L infinity, this is L1. So by dominated convergence theorem, limit this is gx. uniformly, of course. And so this is actually 1G. Okay. And hence maintaining to infinity. Okay. One thing, if a sequence un in L to R, this converges weakly in L to R, then obviously the sequence regarded as the tempered distribution converges weakly. Is the converse true? Actually, the converse is not true. You can consider some examples. Now, continuity of differentiation. Okay. So we have seen that a sequence Fn in Schwarz space, convergence in Schwarz space is a very strong notion. Okay, very strong notion, and we know that if Fn converges to F in SR, then a sequence of derivatives Fn dash converges to F dash in SR. So what about in weak notion? So here for tempered distribution, that so theorem suppose un is a sequence tempered distribution converging weakly to U. The sequence U dash. Proof is very simple. So un is a sequence of tempered distribution converging weakly to U, and then the sequence un dash, that sequence of derivatives un dash converges weakly to U dash. So okay, so to show the convergence weakly, so yeah, let G belongs to SR, be arbitrary. So consider un dash G. This is what? So if you integrate by parts, so this is basically okay. So this is what? dun dash x dx gx dx. Un x minus infinity minus r g dash x un x dx. And since gx is in SR, so limit mod x tending to infinity gx 0. So this first term is 0 minus this. This is what? This is basically un comma g dash, and this is this converges to, since un converges to u weakly, so this is un is to g dash minus, and again this is by reverse way, using by parts, you will have this minus minus plus u dash g and tending to infinity. So un dash u dash weakly as n tending to infinity. Okay, this is done. So from these, does converge weakly to 0? Yes. Why? Already we have seen 0 weakly as Newton into infinity. So sorry, this is cos mu x. What is the derivative of this? So 0. So by above theorem, so derivative this new cos x mu x and 0 derivative 0. Now recall the Fourier transform was continuous operator, right? As an operator, continuous operator on SR, and we now establish sequential continuity of the Fourier transform as an operator on the space of tempered distribution. So that S dash R. Okay. Continuity Fourier transform theorem Suppose u nu is a sequence tempered distribution converging weakly, then the sequence converges proof is similar like differentiation, and okay, let us see. Okay, so let first G. Yes, sir. Arbitrary. Consider un hat not un nu at G. So R now by Fourier's theorem, e to the power I x y dx dy, right? And this is G hat G hat y dy, and this is exactly same as u nu G hat, and this goes to u G hat, and this is same by reverse way using this by Fourier's theorem. This will give you G hat u. Sorry, u hat G. Thus, so as Newton infinity, thus okay. So using this theorem, we can solve some problem. Find the weak limit of limit 0 plus minus x square by 4 epsilon. Okay, so cleverly you have to look on this. Okay, uh, so see, so your previous theorem was what? So u knew a sequence of tempered distribution converging weakly to u, and then the corresponding Fourier transform of sequence u knew hat. This converges weakly to u hat, right? So can you guess, is this a Fourier transform of some function? Actually, yes. So this is basically e to the power minus x square by epsilon hat. This is your root pi by root epsilon exponential. So instead of exponential, you can write e to the power minus. So self transform actually, yeah, 4 epsilon. Okay, now we can think for this, the convergence for this sequence only, as epsilon tending to plus 0 plus. Okay, so now as epsilon tending to 0 plus, this minus x square by epsilon goes to 0 point wise. For all x. Okay, nice. And so then and also one thing, first of all, this is a tempered distribution. Why? Because this is your vanishing at okay, plus minus infinity, and also this is in L infinity R, so that's why this is tempered distribution. So now wait a minute. Now we have to show what we have to, so let G belongs to SR. This is be arbitrary. Then consider this inner product e to the power minus x epsilon g. So this is equals to your e to the power minus x square by epsilon dx. And so how to deal with this? Again by dominated convergence theorem. So this is pointwise goes to 0, and this gx, so this total fnx e to the power minus x square by epsilon, so this is basically modulus gx, and g belongs to your SR, so in L1R, and so g is integrable, and so by dominated convergence theorem, this limit epsilon tending to 0 plus sorry, this e to the power minus x square by epsilon comma g, this is limit epsilon tending to 0 plus r gx e to the power minus x square by epsilon dx, this goes to 0 as 0 plus by dominant convergence theorem. Since this is pointwise to 0, and this is in L1R, that means integrable, so goes to 0, and this is your 0 comma g for all g belongs to SR, and as not as, so this is actually equals to no problem. Hence this e to the power minus x square by epsilon goes to 0 quickly as epsilon to 0 plus, and then this by above theorem 0, so weakly and this is root pi by root epsilon e to the power minus x square by 4 epsilon, this goes to 0 weakly as epsilon tending to 0 plus, is done. So weak limit epsilon tending to 0 plus root pi to the power minus x square by 4 epsilon 0. Okay, I hope it is clear to everyone. Now we'll see one theorem. Okay, so the theorem is basically the locally integrable function and 4 pi square. This both this both are defined temper distribution on R3 via the prescriptions this. And further, the Fourier transform of okay. Now let us revisit the theta function and then Poisson summation formula in the context of distribution. Okay, and okay, let us see the theta function. If you try to find the Fourier expansion of the periodized function direct distribution, then you will have this pi by 2 sum n equals to minus infinity to infinity minus 1 to the power n delta pi n k equals to 1 infinity cos 2k minus 1 x. Now take gx exponential minus tx square which is in Schwartz class, right? For t greater than 0, of course. So so just applying both sides of this gx cos 2k minus 1x dx, and pi by 2, this will be n equals to minus infinity minus 1 to the power n, and this integral will gives minus t pi square n square. So this will survive when only x equals to pi, and okay, so yeah. Okay, now this can be rewritten okay. So pi by 2 is there, right? So just 2 times pi 1 plus, so here 2 and here cos, we can write this exponential e to the power ix plus e to the power minus ix divided by 2, right? So then these two cancel. Okay, right now minus 1 to the power n minus pi t pi square n square. Okay, and equals to right hand side minus infinity to the power minus tx square e to the power ix 2k minus 1 pi, sorry, plus e to the power minus this is by 2. So this 2 and this 2 can be cancelled. Oh, cancel out. Okay, and this is actually, if you see closely, this is 2 times minus infinity to infinity is 2 times Fourier transform of Gaussian. Okay, so 1 plus 2 infinity 1 by root pi t exponential minus 2k minus square by 40. Okay, 4 pi square t. Yeah, so clearly this is okay, and yeah, it's okay.